Alrighty, in this video, we're going to be talking about two measures of variation. So our second objective in this chapter is to describe data using measures of variation, such as the range, variance, and standard deviation. So let's jump right into the first example. So example 10, talking about fading time of outdoor paint. We're going to consider a sample of time in months. Two brands of outdoor paint last before fading. So brand A, 10 months, 60 months, 50 months, 30 months, 40 months, 20 months. Brand B would be 35 months, 45 months, 30 months, 35 months, 40 months, and 25 months. So we're going to compare these two sets of data. So to do that, we're going to calculate the sample mean time in months to fade for each brand. All right, so again, to do this, we just simply add them up. So for mean brand, I wonder if I can have this up at the same time. There you go, perfect. All right, so again, I'm going to pull up my handy dandy calculator, and for brand A, again, notice this is just a sample mean. So that's why it's a capital X, so make sure you keep a note of that. So for brand A, that'd be 10 plus 60 plus 50 plus 30 plus 40 plus 20. We're going to divide that by 6 because there's 6 of them, and we get 35. So brand A's mean is about 35 months. And let's look at brand B. So it'd be 35 plus 45 plus 30 plus 35 plus 40 plus 25. Ooh, 5. We'll divide that also by 6, and we get 35 as well. So notice that we need more information to describe this data because right now it looks like both of these are correct, or not correct, but both of the same brand is going to average about 35 months before the paint fades away. So let's talk about other types of describing factors, and one of those being called the range. So we talked about the mid-range in the last section. That was again smallest plus largest divided by 2. The actual range is just going to be the highest value minus the lowest value, again denoted with a capital R. So the range is the simplest of the measures of variability to calculate. It is the difference between the highest value minus the lowest. So in example 11, we're going to find the range of the brand A and brand B. All right. So to find the range, I need to figure out what the highest and lowest value is. And when I look at brand A, it had 60 months, where another one had 10 months. So the range of brand A would be about 50 months versus the range in brand B, the highest I had was 45 and the lowest I had was 25. So therefore, the brand B's range is 20 months. So although the means are equal for both brands, the ranges are again quite different. And what could happen here is maybe that 60 months was a skewed data, or perhaps maybe 10 months was a skewed data. So but now we can see there is a huge range between brand A versus brand B. I know what I'm going to get. It's going to average between 45 and 25, but in brand A, I could get a really good paint or not so good paint. So we can see the variability of our data there. The next type of variability you have is population variance and standard deviation. Statisticians use the standard deviation as more meaningful statistics than the range to measure variability. Data variation is based on the difference between each data value and the mean. This is called the deviation. Basically, how many deviations away from the mean are you? So the deviation of 10 from the mean of the sample of time of fading of brand A would simply just be you would take the range. So again, the deviation of 10, so it's telling you the deviation is 10, from the mean of the sample of time would be the mean average, which is 35, minus 10, that would be the standard deviation. So that would mean that you are 25 months. So if you are within 25 and 45 months, that would be between one standard deviation of the mean, plus or minus. So the sum of the deviations of all data values in the population about the population mean without rounding will be 0, meaning that that should be the most accurate data because it's all there on top of each other. To eliminate this problem, though, we squared the deviation, add the squares, and find the mean of the sum of the squares by the total number of data values. This is called the population variance, symbolized with a sigma, lowercase sigma, squared. However, this measure is the square of the units of the measure of data. Statisticians take the square root of what we call the variance and call it the population standard deviation, which is just a regular sigma. So regular sigma here, again, notice we're talking about population, so we're going to have to think about Greek letters here. So we have lowercase sigma equals the square root of sigma squared, which is the same thing as the square root of taking each x value, like we saw a while ago, subtracting it from the mean, squaring that result, adding it all up, dividing by how many are in that population, and then taking the square root of that. So again, x, each individual data value in the population, n, again, capital N, because we're talking about population, it's the population size, mu, again, another Greek letter, is the population mean. Thus, the population variance, sigma squared, would just be this without the square root. Normally, these parameters are calculated using technology because when you have the entire population, we're not going to have time to do that by hand. You'd be here for a few days just to do one question. So we're going to round the population standard deviation to at least one more decimal place than that of the original data. So just like in the mean, if it's all the way to the whole numbers, we're going to round to the tenths. If everything's in the money, then we're going to round to the 10,000s, right? 3 decimal places. All right, so that is population variance and standard deviation. Talking about sample variance and standard deviation. This is typically what you do talk about more, but we can talk more about population if they give us some information as well. So most often the sample standard deviation is used because sample data is available more often than the data of an entire population. So the formula for the sample standard deviation is used to estimate the population standard deviation. So when we calculate our sample, we're estimating that this would probably be around about the population. However, merely using the sample mean, again, notice this is a capital letter, so X bar, instead of the population mean, mu, notice the difference between sample and population, and the sample size n, again, notice lowercase n when talking about sample, instead of the population size, capital N, this would underestimate the population standard deviation. Therefore, to calculate an unbiased estimate of the population variance or population standard deviation, we're going to divide this by n minus 1 to hopefully give us a better accurate reading. So the only difference between population and sample is in sample, we're going to have that n minus 1 at the bottom of our equation versus just having an n. Other than that, it's still pretty much the same. This is actually missing a little symbol here. Where's my little marker here? This should be x minus x bar. Put that right here as well. Maybe it's just a notation thing. Maybe I just couldn't read it. But that, again, just like the population, it's going to be each x value minus the mean squared, add up all those numbers, divide that by n minus 1, that's the only difference, and then taking the square root. The variance of the sample, again, also a couple things to note, is standard deviation for sample is an S. Again, Roman letters are just regular letters to us, no Greek letters here. And so therefore sample variance would be S squared. All right. So that's a lot of talking. So let's actually do some calculating. Give you an example. So in example 12 here, we're going to find the sample standard deviation from brand A of the paint. So find the sample standard deviation for brand A listed in example 9. Recall the sample mean for brand A. I'll pull this back up for y'all, was 35, right? So to calculate all this, we need to do this value minus 35. So let's do that. So we have 10 minus 35. So we get negative 25. We'll do 60 minus 35 and we get positive 25. Fifty minus 35 and we get 15. We will do 30 minus 35 and we get negative 5. 40 minus 35 and we get positive 5. We will get 20 minus 35 and we'll get negative 15. Now we're just going to square these numbers. So negative 25 squared is actually 625. Don't believe me? Do 25 times 25. Also note, anytime you're squaring these numbers, you should get nothing but positive numbers. Anything squared is always positive. So this right here would also be 625. This would be 225. This right here would be 25, 25, and then 225. All right, so now that next little part there is to now add those all up. So let me add these all up. So 625 plus 625 plus 225 plus 25 plus 25 plus 225 gives me 1,750. All right, so now that we have that, now we can use this information to find our standard deviation, sample standard deviation. So we'll do the square root of this result of 1,750. N minus 1. Well, there was 1, 2, 3, 4, 5, 6 samples. So 6 minus 1 would give us 5. So now I come over here. I take that 1750, divide it by 5. And then if you just hit this little square root button, it'll take the square root of it for you as well. So my sample standard deviation is 18. Again, all this went by whole numbers. So I'm going to go to just the tenths. So this would be 18.7. They call this a shortcut formula as well, where you can actually square all of these numbers, add them up, then add all of these numbers, take that number squared, subtract the 2, and then divide that by the 6 times the 5. I'm going to be honest with you. I have never found this formula to be a shortcut formula because you're still doing just as much math. You still got to, square them all, still got to add them all. You still got to multiply by another n there because there's an n right here. It just seems like that just seems more work where I feel like this is a lot quicker. So the book will tell you this is a simple way. That's crazy to think of that. So I'm just going to stick with this. But again, if you wanted to know how to do this, you would do 10 squared plus 60 squared plus 50 squared plus 30 squared plus 40 squared plus 20 squared, get that sum, multiply that by your 6, which is your sample, subtract that from 10 plus 60 plus 50 plus 30 plus 40 plus 20, whatever that sum is, squared, subtract it from the result you just had, then divide that by your 6 times 5, and then take the square root of that. So they can call it simple if they would like. Okay. So what we'll do too is we'll show how to use this in the calculator. Right now, it's pretty easy stuff, but it'll get a lot harder. So in our Inspires, if you actually go to list and spreadsheets here, what I'm going to do is I'm just going to type in my information in that first column. So that's 10, 60, 50, 30, 40, 20. Now there's my 6 numbers. If you then go to menu, 4 for statistics, you want to do stat calculation, you want to do your X. That's not what I chose. Hold on. Let me do this. Menu, 4 for statistics, 1 for stat calculations. There we go. And then we want to do 1 variable statistics because we're only comparing 1 variable. We'll get into 2 variables down the road, but you just hit 1. Number of lists is simply just 1, and then hit OK. I want to take the list from A, and I want to put the results in B. All right, so we'll just hit OK here, and then we get our data. So what you'll see here is it gives us our X bar, our mean, which was 35. It went ahead and added all those numbers and got 210, squared all those numbers, added up, got 9100. It did what it calls its simple form. But then we see all of this information here. So it gives us our sample standard deviation of 18.7, and then gives us what they think the population standard deviation would be, which is 17.07. But really and truly, you just want that SX. You don't want the population. Even tells you how many your N is, what your minimum. We'll talk about quartile 1. It gives us the median, which was 35 too. It talks about quartile 3. It tells you what your max value is. So if you need to find your range or anything, again, this number, we'll talk about these numbers as well. Oh, this number is the number that you use before you divide it, that 1750 that we calculated. So if you kind of go over here, you can see the equation right there. The x minus x mean squared, and then the sum of all those. So the calculator does a lot for us. And again, with just 6 numbers, it wasn't so bad for us to do the math ourselves. But if I was to give you 30 numbers, let's say we were doing those coaches again, that would take you quite a bit of time when the data can just be pulled here. The issue is you need to find the correct data. So if I want the sample standard deviation, I need to know that S, lowercase s, is my sample standard deviation. So this would be my answer. I do not want the population because it's assuming. So what it does here, the calculator doesn't know if your data is a sample or a population. So it assumes first that it's just a sample of a population, so it gives you that. But then it goes, well, if this is the population, then this will be the answer. And remember, the difference of the formula was you either divide it by n for population, and then for sample, we would divide by n minus 1. So there will be a difference in the answer if this would have said, hey, this is the population. So just make note of that. You wanted this when talking about the standard deviation. All right, so now that we know how to do this, let's find out what the standard deviation of brand B is, but let's use our calculator. So what I like to do is I like to open a new spreadsheet if I'm doing different data so that it doesn't skew any of my data. I need to go find the original B stuff. Oh, there it goes. All right, so brand B is 35, 45, 30, 35, 40, and 25. All right, so there's our 6 numbers. And again, to recall, this will again be menu. For me, I'm just going to type the numbers because earlier I tried to click on it and it took me to the wrong thing. So then I'm going to go 4 for statistics, 1 for stat calculations. We only have 1 variable we're looking at, so this will be a 1 variable statistic. I just have 1 list. There's not multiple lists here. I'll hit OK. I want the results from the column A to go to column B, so I'll hit OK. And again, we can see our data. The average again was 35. We've already calculated that. It gives us these quick samples if we wanted to use the quick way. And again, notice again, SX, this is the sample standard deviation versus the population standard deviation, but we know this is a sample. Gives us our N minimum. Again, I'll talk about the quartiles. Gives us the median, the max. Again, remember, we can use the minimum max to either find range or mid-range. And then gives us that total had we done this by hand to divide that by 5. So therefore, again, that's the number that we were looking at, which is the 7.1. Again, we were going to round to 1 decimal place. So again, there's your stuff. This is, again, your textbook uses the 84. So if that is what you have, follow those steps. I like the Inspire. Heck, you can even use Excel. This is just on the test. You won't be able to open up an Excel. So have a and some type of calculator. All right, so again, we found the new standard deviation of brand B, and it was 7.1. What does this indicate about the variation of the two brands? Again, we can see that although both brands had the same average, the very, oh man, getting ahead of myself. I was thinking about the second sentence. The same average, the brand B has a more consistent time frame since it has a lower variation. Remember, variation just tells you how broad your data is. The smaller your standard deviation is, the less variated your data is, which is good. We want that standard deviation to be as small as possible because that means our data will be all pretty much the same. If we have a large standard deviation, then our data is really spread out and we have a very large variation, which is not that great. All right, so again, like the note you saw the standard deviation denoted with an SX, that again, that lowercase s, that's really what this should be too, but that S right there indicates it's a Roman letter, so it's talking about sample. If this was again population, you would have saw that sigma SX. So if I would have told you, hey, this is brand A's population, this is every house they've ever done, maybe they're brand new, then I'm looking for the sigma. All right, so with that, uses of the standard deviation. So the standard deviation provide measures of spread or variation. So really into spread would be the best word. So spread, but you could also say variation of the data. So if the standard deviation is large, the data are more dispersed or spread out. It is used to compare the variability of two or more data sets. So again, we compared brand A and brand B to see which one is less variable for, I guess, variability. What's closer to the mark, right? So number two, the standard deviation is used to determine the consistency of a variable's value. We also saw the standard deviation is used to find the number of data values that fall in a specific interval in a distribution. We'll talk about that here in a second. And then number four, the standard deviation is used in inferential statistics as well. And we'll talk about that. So what we can do is, I'll just give you a stem bit of this. We can use the standard deviation to infer about our data to give us a idea of what kind of information we can pull from it. All right, so let's talk about our coefficients of variance. So our coefficient of variance is a statistic that allows comparison of standard deviations of data sets having different units, such as variable measures in inches and a variable measured in centimeters. So the formula for the sample coefficient of variance, also known as CVAR, is expressed as a percentage. So a sample CVAR, you would just take the sample standard deviation divided by the sample mean times 100. This will just give you basically, again, this gives us a comparison looking at percentages. So like I said, if we're looking at the comparison of how plants and trees grow in the same soil, one might be in feet, one might be in inches, but we can compare it with the same looking data, but just turn them into percentages. We can see the growth factor here is this kind of percentage. The growth factor here is this type of percentage. If you have a population CVAR, you would just take the population standard deviation divided by population mean times 100. And again, I cannot express this enough, but do note the different symbolism for sample, again, using those Roman letters or R typical letters, and then population using those Greek letters. All righty. So if needed, and you need the coefficient of variance, that is how you would calculate it. A range rule of thumb. So you can actually calculate a rough estimate. So if you didn't have time to calculate all of the data, you could actually come up with a rough estimate of the standard deviation for a sample by simply taking the range divided by 4. So if you just figure out what the highest value is divided by highest value minus the lowest, and then divide that result by 4, you can get a rough estimate. So on your homework, it's going to ask for a rough estimate. This is how you calculate it. All right, there is a Chebyshev's theorem here. So the standard deviation of a variable measure, spread, or dispersion of the variable, the larger the standard deviation, the greater the dispersion. The smaller the standard deviation, the less the data values are dispersed and the data values are more consistent. Chebyshev's theorem finds the proportion of spread in terms of standard deviation, and the theorem applies to any distribution regardless of shape. So that's a descriptive way, but basically really what it is, it's just the proportion of values from a data set that fall within K standard deviation. So however many standard deviations you want to be. So if you want to be 2 standard deviations away, K equals 2, which would just mean at least 1 minus 1 over however many standard deviations you want. So if you wanted 2, you'd plug in that and you'd get 1 minus 1/4. So that would be 0.75. So 75% of your data should fall between 2 standard deviations. And that's really all that means. Maybe you wanted to just be 1 standard deviation away. So you'd plug it in with 1 and you would have, oh, well, sorry, it has to be greater than 1. So maybe you want 3. That would be what, 3, 9, 1, 9, 2. That would be 8, 9. So about 87%, no, 89% of your data would be 3 standard deviations away. But that's just a calculation of how much of your data should be within a certain amount of standard deviations. And we have a better chart for that as well. We'll see later down the road. But let's look at this example here. So in example 13, we're going to talk about hours online per day. So Americans spend an average of 2.85 hours per day online. So if the standard deviation is 32 minutes, we're going to find the range in which at least 75%, that is when K equals 2 standard deviations, and 88.89%, that is when K equals 3 standard deviations of the data. So first thing you want to do is change the average to the same units. So let me bring this back up. Trying to see if I can I don't think I'm going to be able to. Change the average of the same units as the standard deviation is. So Americans spend 2.85 hours. So what we'd want to do is turn that into minutes since our standard deviation is that. So 2.85 times 60 gives us 171 minutes. So this is 171 minutes. If the standard deviation is 32 minutes, we're going to find the range in which at least 75% and 89% of the data will lie. So again, 2.85 hours is 171 minutes simply by multiplying 2.85 by 60. So again, if I want to know the k equals 2, again, it told us here, but this is what I was just explaining a while ago. This simply is just 1 minus 1 over 2 squared, which is 1/4. So you get 3/4, which is 0.75, which is 75%. So 2 standard deviations, plus and minus, should contain 75% of your data. So the way we're going to calculate that is you're just going to do the mean. So this is the mean, this is the average, plus however many standard deviations you want. So in this case, 2. So this would be k times that sample standard deviation. Again, I'm assuming, it doesn't tell me population, that it's going to be just a sample. And then after that, you just do the work. So 2 times 32 is 64. And then when we add those up, we get 171 plus 64, which is 235 minutes. Or if you want to put that back in hours, we would simply just divide that by 60. And that would roughly be, let's see, we'll go 3.92 hours. All right, so let's kind of pull the rest. I know y'all, I can't see it here, but y'all can see on y'all's page. So again, when I say plus or minus, this would be if the average again is 171 minutes, 75% of your data on the right side would be 235, but now you need the left side. So the way we do that is we do 171 minus 2 times whatever the standard deviation is. When I come over here, I'm going to do 171 minus 64, and I get 107. And again, if I wanted to put that back in hours, I would just divide that by 60, and I see that's 1.78 hours. So 1.78 hours. All right. So again, what this is basically stating is 75% of the Americans of the population, we're in a state, or the sample, however this is looking at, fall between watching TV for 107 to 235 minutes a day, or sorry, online, not watching TV, online. So that is what that's stating. So 75% of Americans will be watching TV or watching online stuff from 107 to 235 minutes a day. That is what that is stating. So if I wanted to know 3 standard deviations, which again now would be about 89% of my data. So now again, this one, so thus again, to kind of fill this out, using Chebyshev's theorem, at least 75% of the data again would fall between the 1.78 hours and the 3.92 hours. So that's how much time 75% of Americans spend online, give or take. So now if we wanted to calculate the 89%, again, the way they did this, using this formula, they plugged in the 3 right here. So 1 divided by 3 squared is 1/9. So 1 minus 1/9 is 8/9. 8/9 as a decimal is 0.8 repeating. So they come out to about 88.89%, which I usually just round up to 89%. So what we're going to calculate is, where does 89% of Americans fall within a range? So now we're getting those outliers out there that might have been, maybe we don't know how to use the internet. Maybe that's all we do is use the internet. So notice the equation now just changes to 3 times the standard deviation, because now I want to know 3 standard deviations away. So when we calculate this, I get 171 plus 96. So that gives me 267 minutes. Again, if I want to do that in hours, I would simply just divide that by 60. So that's 4.45 hours. And then vice versa, if I want to find the left side of the data, so this is the highest part of the 89%. The lowest part would be 171 minus 96. And then we're going to divide that by, hold on. 171 minus 96 is 75, sorry. Now we're going to divide that by 60, which gives us 1.25 hours. Right. So therefore, now I can argue that 89% of Americans watch online stuff for between 1.25 hours to 4.45 hours a day. Right? And that's basically, again, what that is stating. So this would have been between 1.25 and this number over here would be like 4.45. All right, so that's using Chebyshev's theorem to get a rough estimate of the amount of data and where it should fall. This is not saying that's where it is going to fall, but we can roughly say this is where it's going to fall at. All right, so let's look at example 14 now. Example 14 says average time to traverse a maze. So the average number of trials it took a sample of mice to learn to traverse a maze was 12. The standard deviation was 3. So using Chebyshev's theorem to find the minimal percentage of data values that fall between 4 and 20 trials. So if we know the equation for Chebyshev's is 1 minus 1 over k squared, right? That's his formula. And so when we want to use this to find out how many standard deviations away, we would do the mean minus standard deviations times, so k would be the number of standard deviations times this, and then that would equal my result. So what's happening here is we have to now use this formula to help figure out, all right, how many standard deviations is 4 and 20? So for 4, again, I can set my average, which was 12. So this is going to be 12 minus, because we're going to look at the left side of 4, because since 4 is the left side of the mean, this would be the plus side of the mean. So I'll do minus, where we know standard deviation is 3, so it's really k times 3, but in mathematical sense, we write it as 3k, and we know this equals 4. So to solve this, we'll simply just subtract 12. So a little algebra in here. So we'll do 4 minus 12, and we get negative 8. And then we'll take this negative 3k equals negative 8, and we're going to divide that by negative 3. Oop. So divide that by 3, which would be negative. Where's that little icon? Oh, there it is, right? Now make it a negative 3. So therefore, I get the 2.67. I think they just keep it as a fraction. Doesn't really matter. However your homework accepts it, I think they accept it as a fraction as well. So your k there would be 8/3, which is roughly 2.67 standard deviations away. And then again, same process here. You would just do 12 plus 3k, because again, 20 is on the right side of the mean, and this would equal 20. So now I'm going to subtract 12. I get 3k equals 8. Divide that by 3. So I get 8/3. So I'm again between 4 and 20 trials. Just so happens to be plus or minus 2.7 standard deviations from the mean. So that is all the data that should fall in between that. So now that we know what k is, now we can use Chebyshev's theorem as 4 and 20 are the same number of standard deviations from the mean. So here we go. So let me get that up for y'all. So now that I know my K value, they're both the same. I can now come over here. I can say this is now 1 minus 1 over 8/3, because I now know my K, squared, right? Now we just got to figure out what this is as a percentage. So here we go. So I'm going to do, let's see, best approach. Probably going to use this calculator here. So I'm going to use my Inspire and go to regular calculator, and I'm going to do 1 minus control divide. Oh, that did not give me what I wanted. Control divide. There we go. 1 over. I'm going to do control divide again. So I do my 8/3. And since I'm still on the bottom of that fraction, I'm just going to hit the square button. So now it squares that outcome for me. I hit enter. I get this right here. I need that as a decimal. So I hit up to highlight it, hit enter to copy it. I'm just going to move into one of the decimals to make it a decimal. So I put either the top or the bottom. It doesn't matter which one. But when you do that, it produces a decimal. Now all I'm simply going to do is hit times 100, and now I can have a percentage. So now I come over here and I now know that I have 85.9%, or roughly 86% of my data. So I can now see if I get a K value of 8/3, I have about 86% of my data will fall between the mice getting the trials solved between 4 and 20 times or attempts. Okay, so that's using Chebyshev's theorem. Lots of good examples there. So let's move on to the next topic, which is talking about the empirical rule, or what we call the normal rule. All right, so while Chebyshev's theorem applies to any distribution regardless of shape, the empirical rule, which is what we'll typically be using most of the time, applies to bell-shaped data. So by the empirical rule, for a distribution that is bell-shaped, approximately 68%, again, these numbers are going to be very important for you to remember. So approximately 68% of the data values will fall within one standard deviation of the mean. So plus or minus one standard deviation of the mean, 68% of the data will fall there, as long as we know it is a normal bell curve. Two, approximately 95% of the data values will fall within two standard deviations of the mean. So again, 95% fall between the plus or minus two standard deviations. And then approximately 99.7% of the data values will fall within three standard deviations. So within three standard deviations of the mean, majority of all my data should have fallen. In between all that, the 0.3 could just be my little outliers that don't fall quite in there. So this is a normal bell curve. So see how it's nicely even. So when that happens, I can say, all right, well, 99.7% of my data falls between these three standard deviations. And that mean is perfectly in the middle. So a lot of times we'll just tell you, hey, this is a normal bell curve, so that you don't have to go calculate to figure it out. We'll just tell you it. So let's look at example 15 here. We're going to look at the average math and reading SAT scores. So the average math and reading SAT score in 2014 was a 10-10. Suppose the distribution of scores is approximately bell-shaped. So again, it tells you that. And the standard deviation is approximately 86. Within what boundaries would you expect 68% of the scores? What percentage scores would you expect to be above 1,182? So in this part here, if I would expect 68% of my data values, again, to fall within plus or minus one standard deviation of the mean. So the upper boundary here, and then notice here, this is the average math across the world. So notice our notation here, this is population. So my population mean was a 10-10. And now I'm going to add my standard deviation of 86. So that means my upper boundary falls at 1096. And then I'm going to do 1010 minus 86. So that's 1010 minus 86. And I see that's a 924. So I can see in 2014, 68% of my data I expect to fall between a 924 and a 1096. So 68% of the people that took the test will either make between a 924 and a 1096. So that's using the empirical normal review. Now, knowing that exact thing, let's calculate what percentage score would you expect someone with the 1182 get. All right, so let's play around with that real quick. Let me get to y'all's notes. So to find the percentage of scores above 1182, we're going to find the number of standard deviations the value is from the mean. So again, we don't know how many standard deviations it is, but we do know that 1010, again, this was the mean, plus, again, this is like your K, how many standard deviations, times the amount of standard deviation, which was 86. So if I was to multiply this, if I knew how many my standard deviations was, I would get 1182. So what they do now is they take this mean and now they're going to subtract it. And when they do that, you get 172, but you're still equal to this K times this standard deviation. And so now what they're going to do is now simply divide both sides by 86. And so I can see 172 divided by 86 gives me 2. Therefore, I'm 2 standard deviations away. So now using the empirical rule, not Chevy Chev's rule, but empirical rules, we expect 95% of the data within 2 standard deviations of the mean. So that means 5% is evenly split among the data values. So again, here's your stuff. This is my version of it. If this is 2 standard deviations away, so we'll say mean. So this is 1, -1, -2. So this data right here is 95%. That means 2.5% are on both sides to make a perfect 100. So if we split between the amount of data values above and below the means 2.5% of the data is expected to be above 1182. So we were basically saying 2 standard deviations. This is my 1182 when my mean was 1010. So that means any number that's above 1182 will represent 2.5% of my data. So we can calculate that knowing what our empirical rule is. And just like in the last video, I'm going to chunk this up. So this is going to be the conclusion of this video for 3.2. And then the next one, we'll discuss 3.3, which is measures of position. Until the next video.